We will continue our discussion on principle of hydraulic machines and system design. Today we will talk about the characteristics of H cube curve of a positive displacement pump, and we will work out a numerical problem. So we have discussed about the H cube characteristics curve when we have discussed about the operational principle of the PD pump. Rather, we have taken an example the working principle of a reciprocating pump, because reciprocating pump also a class of which falls under the category of PD pump, rather positive displacement pump. I said that apart from the reciprocating pump, there are many other pumps like screw pump, vane pump, gear pumps. Those also falls under the category of reciprocating pump, positive distance pump. But reciprocating pump also a class of positive displacement pump. So we have discussed about the H cube curve, but today again we will recapitulate that curve, and we will work out a numerical example. So if we recall that normally we have taken example of reciprocating pump. Reciprocating pump, which is a class of positive displacement pump, and we have discussed about the working principle, how this pump works. It sucks, the pump sucks fluid from the sump, then it discharges to the delivery tank, and there is a suction stroke and delivery stroke, and which is connected by a crank and connecting rod mechanism. So the linear motion of the piston is now created by the crank and connecting rod mechanism, and it also depends upon the pump performance, also depends upon the frequency of the rather rotation of the crank speed. And we have discussed that if we try to draw the H cube curve of a PD pump, so the H cube curve look like this. So this is the discharge, this is the H, so this is discharge, and this is head. So if we try to develop the H cube curve for this kind of pump, then how we will get it? We have discussed that the PD pumps, positive displacement pumps, are this head cube H cube curve is like this, that normally these pumps these pumps are used, this class of pumps are used to deliver high head against a almost constant flow rate. So this is the characteristics feature of the positive displacement pump. So it is normally used to deliver a high head against a constant head, flow rate remains almost constant. So that means if I draw the H cube curve, the curve like this. So as I said that this is again, so this is again a theoretical one. So this is theoretical, rather ideal, but we have discussed that normally whenever it discharges, when delivery strokes, when piston moves from the open end of the cylinder to the closed end of the cylinder, then it discharges water to a delivery sump, and then high pressure develops. Because of that high pressure, there is a leakage of some amount through the glands, and as a result of which we get actual curve which looks like this. So this is the actual curve. So this is the actual curve because of the leakage through glands. So this is the H cube curve, and that is why we have defined one efficiency that is called volumetric efficiency, and we have obtained that volumetric efficiency is basically actual discharge by the ideal discharge, and then we have defined one slip factor, that is there is some amount of leakage. So Q theoretical minus Q actual divided by Q theoretical, so 1 minus eta V, that is volumetric efficiency, that we have discussed in the last lecture. Now today we will work out one example. So, how we can solve a particular numerical problem for reciprocating pump, this is very important. So, we will take an example now and we will see how we can solve this particular problem, and we will write the problem and then we will solve the problem considering the theoretical analysis that we have carried out in my last lectures. This is very important. So, first we write the problem and then we will slowly proceed to solve that particular problem. So, this is all about the H cube curve. Now, if I go to the next slide and if I write the problem, so problem is like this. Find the maximum speed of a single acting reciprocating pump to avoid separation, which occurs at 3 meter of water, which occurs at 3 meter of water. This is absolute. The pump has a cylinder of diameter. The pump has a cylinder of diameter 10 centimeter and a stroke length of 20 centimeter. A stroke length of 20 centimeter. The pump draws water from a sump. The pump draws water from a sump and delivers to a tank, The water level in the sump is, it is written, the water level in the sump is 3.5 meter below the pump axis, and in the tank the water level, the water level is 30 meter above the pump axis. The water level is 13 meter above the pump axis. The diameter and length of suction pipe, it is given that the diameter and length of suction pipe, are 4 centimeter and 5 meter, while of delivery pipe the diameter and length are 3 centimeter 20 meter respectively, 3 centimeter and 20 meter respectively. take atmospheric pressure head, take atmospheric pressure head is equal to 10.3 meter of water. So now we have to solve the problem. So if to solve the problem, we need to draw the indicator diagram. Probably we have discussed about the indicator diagram, the ideal one, then modified the inertia pressure and then the frictional effect. So if we try to recall the indicator diagram, then indicator diagram looks like this. That so this is the solution. Rather we solve the problem in the next slide, or we can start here also. That if we draw the indicator diagram, this is pressure, absolute pressure, this is also the volume. Then indicator diagram is like this. We have this is the atmospheric pressure. So this is H atmospheric. Then we have the ideal one, and then we have modified with inertial pressure, and then we have frictional effect. So this is HS suction, and this is only to take the effect of, and this is HFS. So this is HFS and this is HAS. Similarly, this one, so this will be the HFD and this will be HAD. So we are calling it. Now this is the indicator diagram modified with different effect like inertial effect and effect due to fluid friction, that is in the suction and delivery line. Now what is inertial pressure? So inertia pressure, that is where we have solved Pi that equal to rho L dV dt. That is what we have written. Pi is equal to rho L dV dt, and dV dt is equal to, we have written, if you recall, that dV dt will be equal to, I can write A by A is the cylinder area, cross section area, and A small a is the area of pipes cross section area, then R omega square cos omega t. That is what you have obtained. So then Hi, that is head corresponding to this inertial pressure Pi by rho g, that will be equal to how much? L by G A by A R omega square cos omega t. This is very important. So it will be plus minus sometimes. So basically it will be plus minus L by G A by small a into R omega square. This is equal to plus minus because displacement, because crank rotates from 0 to 180 degree, because here I am writing. So since crank rotates from 0 degree to 180 degree. So as I said you that at the beginning and end, so cos omega t will be 0, their inertial effect will be maximum, velocity and fluid frictional effect will be 0. So that is why we have taken 0 degree to 180 80 degree, and then again 180 degree to 0 degree. So that is why you have taken that is plus minus omega t. So we have obtained this is the inertial pressure Hi. Now, so here I can write that maximum speed during, we have to calculate the maximum speed of a reciprocating pump to avoid separation. The maximum speed during suction stroke without separation is obtained from the relation. Now, maximum speed during suction stroke without separation is obtained from the relation H atmospheric minus static Hs minus H separation, that will be equal to Ls by G into A by A suction. Capital is the area of the cylinder cross section, small a is the area of the pipe, suction pipe, into omega square r. So here what is atmospheric pressure, that is given 10.3, Hs that is given 3.5, that is water level is how much, static height, that water level is, that is given that the water level in the sump is 3.5 meter below the pump axis. So this is 3.5 meter, and H separation that is equal to, that is very important because that we need to calculate that separation, it is given that which occurs at 3 meter of water absolute. So this H separation 3 meter it is occurs, that will be equal to Ls is equal to 5 divided by G 9.81 into pi by 4, and it is 0.1 square divided by pi by 4 into 0.04 square into omega square into 0.2 by 2. So I know all the values. So because I know the stroke length I know, so omega square r I know, and 20 centimeter. So omega is equal to, we have to calculate. If I try to calculate, so H ATM I know, Hs the static height that is 3.5 meter and separation that is 3 meter. So if I calculate using this, from there I can calculate omega and speed should be 32.98 rpm. So this is another case. So this is the maximum speed during suction stroke without separation is obtained from the relations. Similarly, you can calculate maximum speed during delivery stroke without separation is obtained. How? Because atmospheric pressure plus we are having static height of the delivery tank minus H separation, that is of course that is there, is equal to LD length of the delivery pipe divided by G into A divided by AS into omega square into R. So again we know everything because this is 10.3 and it is given 13 meter away minus separation which occurs 3 meter of absolute water absolute. LD is given 20 by 9.81 and A is equal to again pi by 4 into 0.1 square divided by pi by 4 into 0.03 square into omega square into 0.2 by 2. So if I calculate from this, that maximum speed during delivery stroke without separation is obtained. So that Hs and Hd we know from the schematic that I have drawn. Hs is static height and then Had is the effect of inertial head, because head due to the inertial pressure and then frictional head. So now if I calculate from this equation, we will obtain the value of n, so I will write in the next slide. So value of n will be that 28.5 rpm. So maximum speed during delivery stroke without separation is obtained is the 28.59 operation. So now the question is find the maximum speed of a single electric reciprocating pump to avoid separation which occurs. So the minimum of these two speeds is the maximum speed of the pump. Now question is the minimum of the two speeds is the maximum speed of the pump to avoid separation, and so that is given. So that is what is the minimum which occurs at the during the delivery stroke. So this is the maximum speed of the pump to avoid separation. So maximum, now I am writing that maximum speed of a reciprocating pump. Maximum speed of a reciprocating pump. So maximum, this is very important, maximum speed of a reciprocating pump is determined from the fact that, I am writing this, from the fact that the pressure in the cylinder during suction and delivery stroke should not fall below the vapor pressure, of the liquid. This is very important. Flowing through suction and delivery pipe. Suction and delivery pipes. So right. So this is important. So maximum speed of a reciprocating pump is determined by the fact that the pressure in the cylinder during suction and delivery stroke should not fall the vapor pressure of the liquid flowing through the suction and delivery pipes, and that is why we have calculated the maximum speed during delivery stroke without separation, because separation occurs 3 meter of water column. So I know the atmospheric pressure head, and this is a static height, this is a separation, and this is very important, L by G A by AS into omega square r. This is essentially the inertial pressure, I mean inertia head, rather I can say this is the inertia head. So this quantity is the inertia head. So this is inertia head. So if I calculate it, I have obtained that the maximum speed in the suction stroke is 32.98 rpm, and maximum speed during delivery stroke is again coming 28.59 rpm. The minimum of these two speed is the maximum speed of the pump that can be used to operate without having separation at the suction side. And that is why we have defined that what is the maximum speed of a reciprocating pump. Maximum speed of a reciprocating pump is determined from the fact that the pressure in the cylinder during suction and delivery stroke should not fall the vapor pressure of the liquid flowing through the suction and delivery pipes. So this is one numerical problem that we have solved for this particular PD pump, and we have derived that how we can obtain this HSF, right. So if we go back to my previous slide, here we have written so this is inertia head. This is inertia head, and this is omega t, because that this is very important at the beginning. Crank rotates from 0 degree to 180 degree. So when it starts maybe suction stroke and it ends, so and again from 180 to 0 degree. So cos 0, that is at the beginning of the suction stroke, it is cos 0. So this is this one, so inertia head. Similarly at the beginning of the delivery stroke, it is again coming to L by G A by omega r omega square. This is plus minus. So considering this, we have calculated that the minimum of this two speed is 28.59 rpm, and this is the speed at which pump can be operated without having separation, and we have defined the maximum speed of a reciprocating pump, and this is very important to know, and for that we have to calculate maximum speed during both the strokes, I mean suction strokes and delivery stroke. So with this I stop here and I will continue in the next lecture. Thank you.